Okay. Good morning, ladies and gentlemen. And I think most of us are here. So hopefully we're ready to start. Okay. So let's try to continue our lecture in chapter 2. Okay. Basically, chapter 2 is mainly focusing on the measurements and the characterizations on solar cells. So we're going to look we're going to look deeper into this topic today. Okay. So last time we started to talk about the measurement standards, for measuring the efficiency of the solar cell. Okay, and basically our basis is the STC condition, and also we try to actually look into why there are these irradiance and the solar spectrum requirements in the STC specification. So we specifically we were talking about the why do we need exactly 1,000 watt per square meter irradiance in STC, and also besides the irradiance requirement, why is it necessary to have the spectrum requirement? Okay, the reason for this is that this is actually one thing we tried to emphasize last time, that each solar cell will respond to different wavelengths differently. Okay, so the reason for this is that the solar cells are based on the semiconductor material, and typically for a single junction solar cell, it has a fixed bandgap, and if the bandgap is fixed, then towards with the different wavelengths incident on the semiconductor, the behavior will be different. And if you recall from solar PV, we mentioned that for long wavelengths photon, we may have the transmission losses. Okay, and then typically, of course, we would like to use as much photon energy from the photon as possible. Okay, that will contribute to the usable portion. But the problem is that for short wavelength photon, especially, part of the additional energy from that photon will have the tendency to be lost from the thermalization losses or thermalizing losses. Okay, so this means that if you have a fixed bandgap from your solar cell, and if you incident the solar cell with the two different light sources, with the two different light spectrum, the end result will be different, even if they have somehow the same irradiance. Okay, so this is actually quite important, I think, for us to understand. And then we look at, I believe that we look at one very extreme cases. Okay, we look at the two light sources. Both consist of a single wavelength of photon, and then incident on a typical silicon solar cell. Okay, so if we talk about very long wavelengths, like in this example, that is beyond the bandgap wavelengths, then obviously from the solar cell, even if this signal has 1,000 watt per square meter irradiance, we will be expecting zero electricity generated from silicon, because this is actually all of this irradiance, they will go to transmission loss. Okay. At the same time, for a visible light for 600 nanometer, this is actually well below the bandgap of silicon. Okay, well within the bandgap of silicon actually. So actually, these photons, they have a very high chance to generate electricity from silicon solar cell. So at this time, this is the perfect opportunity to use the quantum efficiency concept we just learned before. Okay, so from the irradiance, we learn how to convert the irradiance into number of photons. Okay, simply by dividing the photon energy. Okay, photon energy of this specific wavelengths, and then we also need to basically scan the quantum efficiency plot and find the corresponding wavelengths. So we're talking about 600 nanometer. The corresponding quantum efficiency is a little bit above 60%. Okay, so let's assume that this is a 64%, and this means that on average, 64% of the number of photons will be able to convert it into carriers or charge inside the solar cell. Okay, that will give us this quantity right here. Now the last step, we just need to convert the quantity of charges into a current density. Okay, so simply by multiplying the elementary charge. Okay, and at the same time, because we didn't do any unit conversion before, so by default you end up with actually a density unit, because the irradiance is actually a density unit. It's a per square meter. So the number of photons will have also a density unit, and the number of electron and hole pairs will also have a density unit. So actually, in the end, you are not just getting the current, but you are getting the current density, okay, which will also have a density unit at the end. Okay, so this is actually, I think, a key point we talked about last time. I just want to bring this point again, to reinforce this idea for you. And then because of this, we need to use a very specific equipment to simulate the sunlight. Okay, that is the purpose for our sun simulator. And then we look at the different options for the light source from a solar simulator, from a sun simulator. So we have this many options typically, but of course, each option will give us a different, performance, and also they have each of their own limitations. Okay, so the most popular choice for solar simulator is the xenon arc lamp that will give us a very good fit of the shape of the spectrum versus a standard solar spectrum. Okay. At the same time, we have some cheaper alternatives, but usually they will produce a spectrum that is quite different from the solar spectrum. And because of that, typically you have to do significant modification on the lamp. Okay. So no matter which lamp you select, in the end, if you need to simulate the precise solar spectrum, typically you always have to do some correction, typically with optical filters. Okay, with optical filters. And then another requirement we mentioned in solar simulator is the requirement for collimation. Okay, collimation. We would like actually the light rays to be aligned so that they are parallel to each other. So in this way, we will have a very uniform illumination area compared to if you do not collimate the light. Basically, the light rays actually they will tend to scatter. They will tend to not focusing. So you will end up with a very different intensity at a different distance and also in the different spots. Okay, so the collimation requirement, as well as the typically the optical filter requirement, these two features you'll find actually in pretty much every solar simulator. Okay, this is the basic requirements typically for all the solar simulators. And then I think last time we also looked at this example here, so to show you that why the optical filter is necessary. Okay, so the real AMS 1.5 solar spectrum, is actually the black curve. At the same time, we have also a artificial solar simulator that produces a very similar spectrum, but at the end of the day, if you look closely, there will be some significant differences at a certain wavelengths. Okay, so it's this means that this solar simulator is mostly a good solar simulator, but at the end of the day, there will be still some differences. Okay, so the question is, how can we quantify this difference? Okay, how do we judge the quality of a solar simulator? How do we say that this is a poor solar simulator or this is an excellent solar simulator that will give us a very good match? Okay, so roughly speaking, we can try to compare, between the difference between the standard solar spectrum and the actual solar spectrum from your solar simulator. Okay, so there are different ways actually to calculate this difference, such as you could try to add each wavelength. You could try to calculate the absolute difference between the two spectrum. Okay, and then you could sort of integrate the difference over the full range of the spectrum, and then you will get a quantity that will be proportional to the difference. Okay, so there are different ways to calculate the so-called difference here, but in general, we refer to the difference as a spectrum mismatch. Okay, spectrum mismatch. So if you want to say that this is a good solar simulator, of course, the spectrum mismatch, the difference, has to be as small as possible. Okay, and then if you follow the same method to calculate the spectrum mismatch, you can compare between different solar simulators. So this is actually one of the quality we are looking for in the solar simulator. Okay, And besides a spectrum match or spectrum mismatch, what else do we need to look for? Well, typically, these are the three qualities we are looking for in the solar simulator. Okay, so spectrum match, or sometimes a spectrum mismatch, is basically the same meaning. This is actually one important quality. Okay, so specifically, it means how closely the simulated spectrum it is matching with the AMS 1.5 standard. Okay, and then another quality we would like to look for in a solar simulator is the so-called irradiance inhomogeneity. Okay, this is talking about mostly the uniformity of the irradiance of the sunlight or simulated sunlight over a certain area. Okay, we'll have an example in the next slide. And the last requirement is typically the so-called temporal instability. Okay, temporal means versus time. Okay, so besides the homogeneity or inhomogeneity, we would also like to see how the solar simulator irradiance fluctuates versus time. Okay, definitely for a good solar simulator, you should have a very stable output for a long time. Okay, for a long time, for a short period of time, you always have a very stable output. But the chance is that for most lamp, the irradiance or the output will slightly fluctuate actually versus time. So this is another defining quality for the solar simulator. Okay, so depending on which standard we're using, typically how do we rate a solar simulator? Typically, if we follow the IEC standard, for instance, okay, remember, keep in mind that there are different standards with a slightly different values for each grade. So the top rating from each standard, typically we have three grades, three ratings. That is the grade A or class A, and then class B and class C. Okay, and for each quality, we have a slightly different values from each standard. So for the IEC standard, if the spectrum match or mismatch is at a small percentage, right? So for instance, if the mismatch percentage is from 0.75 to 1.25%, then we call this a solar simulator is a class A solar simulator in the spectrum match category. Okay, so class A is the best solar simulator. Okay, and then if your spectrum match is a slightly larger, is varying between 0.6 to 1.4, we will say that this is actually a class B solar simulator. So it's a slightly inferior solar simulator in this category. Okay, and then the worst solar simulator is the class C. Okay, so the mismatch will be up to 2%. So it's quite significant for the class C. And then we, in the second category, we will also do a sort of like a rating for the class. So if the inhomogeneity is around 2% or less than 2%, we say that this is a class A solar simulator in the inhomogeneity category. Okay, and so on. You can define class B and class C. And then for the temporal instability, for the stability versus time, you could also follow the standard here to define whether this is a class A or class B or class C solar simulator. Okay. Now, if you go to the website to select solar simulator, typically they will tell you that this is a class, and then followed by 3 letters. Okay, 3 letters. So typically they follow the same order. That the first letter is referred to the spectrum match category. The second letter will follow the inhomogeneity, while the third letter will follow the temporal instability. Okay, so very often you are going to see on the web page or on the website that the best solar simulator will be a class AAA solar simulator. Okay, this means that the based on the standard that we have chosen, it has a score all top class rating in all the categories. Okay, and obviously the worst solar simulator would be class CCC. Okay, would be class CCC. So typically this solar simulator will have the lowest cost, but of course the performance is actually the worst. Okay, so this is how you define or you categorize a solar simulator. So let's look at the example here. So we mentioned that the second category for solar simulator is the irradiance inhomogeneity. Okay, so let's look at the same equipment we have in the PV lab. Actually, we have almost the same setup in the PV lab here from this company that's called ABET. Okay, so this is a solar simulator. This is a small solar simulator that will be able to produce a 5 by 5 centimeter illumination area. Okay, so if your solar cell is less than 5 by 5 centimeter, then we can actually use the solar simulator to test your solar cell. Okay, and you can see that this is actually the illumination area here. Okay, this is the illumination area here. It is coming from actually the reflected sunlight, reflected light source from the top side. Okay, from the top side. And as we said, the lamp is housed inside. Okay, it is using a xenon lamp inside the solar simulator. Okay, it's using a xenon lamp there. And then, from the specification, actually, they show you the uniformity or non-uniformity mapping within the 5 by 5 centimeters. So this is the 5 by 5 centimeter illumination area. And in this area, they measure the variation of the irradiance at the different spots, okay, at the different pixel. And then roughly speaking, the variation here, it is less than 5%. Okay, it is less than 5%. So you will notice at some points we have a more irradiance, but at other points we may have less irradiance. But overall, the fluctuation is less than 5% here. Okay, so that is actually the same equipment we were using in the PV lab, and we have used this solar simulator to produce the results for several papers by now. Okay, again, this is taken from the specification of the solar simulator. You can see that for the same solar simulator, because we have different standards, right? Before we were showing you the table for the IEC standard. So for the spectrum matching category, you can see that in all standards, this solar simulator belongs to class A always. Okay, but then for actually they shift actually the uniformity to the last category, and then based on the IEC standard or any other standards we have in the market, it's a class B in the irradiance uniformity. Okay, because we just mentioned that it's around its maximum 5% fluctuation. And then for the temporal stability, the stability versus time, in certain standard, it can be classified as class A, but in IEC standard, it's classified as class B. Okay, and then in the last standard JIS, it's class A. Okay, so if you follow this convention here, roughly speaking, you could say that this solar simulator definitely is going to start with the class A. Okay. And then the second letter, depending on which convention you want to follow. If we follow by the uniformity, requirement, then it's always a class B, in the uniformity. In the last category, if we follow for instance, the IEC standard, it's also going to be a B here. Okay, so you could say that this solar simulator, based on the IEC standard, it's a class ABB solar simulator. Okay. Is this clear, guys? So I think Saul is raising his hand. Do you have a question, Saul? Okay. So far so good. All right. So moving on. Okay, let's try to move on from here. I hope that this is clear. So we have another example, but I think by now you got mostly the idea by now. Okay, so let's look at a case from simulation. Okay, there is a website that's called the PV Lighthouse here. Right? It's a very useful website. From there, you can try to simulate the result or the measurement you get from a theoretical solar cell. Okay. With the different light input, with different irradiance input, okay, or spectrum input. So here we are comparing between two light spectrum. Okay, so spectrum A, it is coming from our standard AMS 1.5 global. Okay, and the irradiance is precisely 1,000 watt per square meter. In papers, sometimes they instead of a watt per square meter, okay, they will be using actually the other unit that is a milliwatt per centimeter square, okay, per centimeter square. The thing is that these two units actually they are both of them, they are very common. Okay, you can find I think both versions in papers very easily. But at the end of the day, it's if you do the conversion, it's just 1 milliwatt per centimeter square will equal 10 watt per square meter. So 100 milliwatt per centimeter square here equals precisely 1,000 watt per square meter. Okay, so this is exactly the STC ratings. And then for spectrum B, it's from a xenon lamp. It's from a xenon solar simulator. And then, artificially, we scale the intensity to be also 1,000 watt per square meter. Okay, so these two spectrum, they have precisely the same intensity, the same irradiance. And then, using a reference solar cell, we would like to see the difference in the output. Okay, the difference in the output. So specifically, you can actually see from here, from the website, the simulation will give you the result. So specifically for the short circuit current density, for the standard spectrum, we're getting 34 plus milliamp per centimeter square. But then for the solar simulator spectrum, we're actually getting only 30, okay, 30 plus. And then how much is the difference? If you calculate the difference, actually the difference is actually more than 12%. Okay, more than 12%. Even though from a very quick look, you could say that these two spectrum actually they are very similar, and at the same time they have exactly the same irradiance. Okay, so that is why actually you see that the spectrum match quality, it is so important for solar simulator, especially if you want to do a precise measurement. Okay, because any small mismatch here, they will give you large error. And you can see here in this example, the error is 12%. And if the error is 12% here, how can you use the result here to say that this is actually the STC performance? Because 12% is actually very significant. Okay, it is very, very large actually difference specifically. So this is actually just another example to show you that why the spectrum match it is different, and you should do everything possible to minimize actually the spectrum match whenever you have the chance. Okay, so that is actually another example here I would like to show you. Okay, if you're interested, you can go to this website. I think this website it is still there. At least last time when I checked, and then you can run the different simulation. Maybe some of the simulation will be helpful for even for your projects. Okay, if you have any senior projects that involve, I think the solar PV, this could be useful. Okay, so so that is actually the solar simulator requirement. Now, besides the solar simulator, remember in the STC, we also have other requirements. Specifically, we mentioned that the solar PV temperature should be 25. Okay, so this is talking about things that is beyond the solar simulator, but typically you also need to have them in your measurements. Okay, so if you want to achieve a constant 25 Celsius temperature, you cannot just use the solar simulator and then without any other instruments, because we know that under the light the solar cell temperature typically will rise. Okay, if it's for a short time measurement, maybe this is okay. You do not you just do a very quick measurement using the solar simulator, and then immediately you record the data. So maybe that is fine, because within typically the measurement takes about 30 seconds or 1 minute. So within the 30 seconds or 1 minute, the temperature will not increase too much. Okay. However, if you plan to do long duration measurements, then at this point you do need to consider how can I maintain the 25 Celsius temperature. Okay. And then if you do the measurement outdoor, this is even more difficult, because we know that at the outdoor, the temperature is also going to be very different each time you do the measurements. Okay, so to maintain a 25 constant temperature, typically indoors, you have to use a temperature controller. Okay, such as this one. Okay, such as this one. This is where you expect to position your solar cell, and then you can see here there is a metal plate here for heat conduction. Okay, And then with the controller here, you can set a temperature, and then this controller will either heat up or it will cool down the solar cell to maintain a constant 25 Celsius temperature. Okay, and of course you are going to place your solar simulator here that is providing the illumination. Okay, so this is actually a very important factor for you to consider. What else do we have to consider? What else do we have to keep in mind in order to do accurate measurement? The other side of consideration, typically, actually you cannot see them directly from STC, but if you do the practical test, if you do the practical measurement, you will begin to see the problem. Okay. The other problem, the second problem we would like to mention here is that actually, even if you have the best solar simulator, let's say you have a class AAA solar simulator, but then the problem is that if you switch on the solar simulator today versus if you switch on the solar simulator tomorrow, depending on the lamp, depending on the operating condition, the output from the solar simulator will be slightly different. Okay. Typically with the lamp, you can define actually the spectrum very precisely. If we have a good lamp, if you have a good solar simulator, the lamp will always produce a profile like this. Typically, okay, typically you always get this profile. No matter the operating conditions. But then the problem is that typically there will be some very minor fluctuation from the lamp. Sometimes you are going to get the same shape, but at a slightly higher intensity. Okay. Other times you might get actually the lamp spectrum like this with the overall lower intensity. So remember that basically the spectrum of the lamp will drift up or down. Okay, up and down from time to time. This means that actually the shape of the spectrum irradiance is not changing significantly if you fix the lamp. But then the problem is that the overall irradiance, sometimes it will go up, sometimes it will go down. Okay, so if the lamp is fluctuating, in a certain range, then we do need to have a better method to control actually the irradiance, to fix the irradiance, because remember the first requirement in STC is that this irradiance should be a fixed 1,000 watt per square meter. Okay, and typically the solar simulator, you can control the input. Typically there is a certain input for the current of the solar simulator, okay, of the sun simulator. So typically you have a knob to adjust the current up or down. And then if you do that, basically you are adjusting directly the irradiance, okay? But then, if we know that the irradiance may not be precise, from time to time, how can we guarantee that we adjust to the correct level? So this is when you do need to do calibration, okay? Calibration of the solar simulator. You typically, after you purchase the solar simulator, it will come typically with a reference detector, with a reference solar cell. And then with this reference solar cell, you do need to calibrate the solar simulator from time to time, okay? Ideally speaking, each time you turn on the solar simulator, you do need to perform calibration to make sure that the irradiance is precisely 1,000 watt per square meter. And then, because the lamp is fixed, so the spectrum we produce is going to be at a fixed shape. So this will be the best operating conditions. Okay, so that is the idea here. Okay, that is the idea here. And then another, the last consideration I would like to mention here is that even if you fix the solar simulator, you fix the light source, you fix the temperature controller. Okay, this is all perfect, but at the end of the day, if you need to measure actually the solar cell, especially the efficiency, okay, remember that even if we follow the current density convention, but at the end of the day, we are not exactly measuring current density directly, okay? Because typically from the circuit, we are not getting current density; we're getting rather the current, okay? So how do we go from current to current density? Remember, we have to divide the current by the solar cell area. Now this could be problematic. Okay, this could be problematic because how do you know the area of your solar cell? Okay, and is it going to be a precise measurement or not? Okay, And also, actually, this is something we're going to mention later, that even if your solar cell has a fixed area, okay, but then the slight problem is that you are typically your illumination area, it should be larger than the solar cell area. Now, this will create a slight problem for you because actually the solar cell will be absorbing the irradiance, not just from inside the area, but also from slightly outside of the area, from the edges of the solar cell. So this actually will basically will actually will you could say that this will create the inflation from the irradiance that the solar cell is getting. Okay, so you thought that the solar cell is getting exactly 1,000 watt per square meter, but in fact, the solar cell it is getting more irradiance with your measurement setup. Okay, so this means that actually it's not the area that is not precise, but also the irradiance definition or the irradiance in the efficiency, it is not precise. Okay, so this actually, we combine this consideration into the last point that the solar cell area should be calibrated, should be accurately calibrated, and also we should try our best to eliminate, the additional irradiance from the edges of the solar cell. Okay, so that you get exactly the irradiance from inside the solar cell area. Okay, so these two additional factors, basically, we will talk about them today. Okay, we're talking about them today. So first, let's look at the irradiance calibration. Okay, so we know that the irradiance is directly affecting the current that you are getting. Okay, is there any questions, guys?
Doctor?
Yes, go ahead.
In the previous slide regarding the setup, I've noticed that it is not covered from the sides. Like usually we have this inside a room where lamps are operating, like lights are operating.
Mm-hmm.
So
Mm-hmm.
this will affect our solar cell performance. So I think we have to cover it from the edges, and then so that the lamp, the light like the yeah, the light coming from the lamps itself doesn't come to the solar cell. We just need the lamp simulator. I mean the sun simulator, so that we get accurate results.
Yeah, that's correct. Yeah, that's a good point. Typically, if you are doing the typical efficiency measurement, you do prefer to switch all the additional lamp inside the room. So ideally speaking, you perform measurement in a dark room. Okay, so you do not get the additional interference from the other lamp. But at the same time, I think regarding the last point, the problem is that even if you are just using the solar simulator, but the solar cell itself is not just getting the irradiance from the solar cell area. It is also getting the additional irradiance from the simulator, but from the area actually beyond the solar cell area. So if you it's not just a problem of irradiance because specifically so your solar cell is getting more you could say solar power than it deserves to get. Okay, specifically from the edges. Okay, from the edges. We do have, I think, I can show you maybe the slides we're going to talk about very soon. That will give you, I think, a better idea. Okay, so imagine that this is your solar cell here. Okay, so actually let's look at actually the picture on the right. I think this is the case if you don't offer any kind of additional adjustment. So if this is your solar cell, but then the light typically the illumination is larger than the solar cell. So the problem is that you are not just getting the irradiance from inside the solar cell area, but also from outside of the solar cell area. Some of these irradiance they will also enter the solar cell. Okay, and this irradiance they will produce additional currents, and that will inflate your current measurement. So this is actually another source of error. Is this okay?
Yeah, it's fine. I think another issue is that the like we can get like light illumination from the lamp itself as 1000 watt per meter square, but the incident light is not 1000 watt per meter square. Like for example, I've noticed in the solar PV lab when we were doing the experiments, even though we have lamp like the overhead, like just above the solar cell, and we put it horizontally, sometimes the lamp itself is tilted. So we are not getting accurately 1000 watt per meter square. So I think we need measurement sensor to make sure that the incident irradiance is 1000 watt per meter square. Am I correct or not?
Yeah, that's correct. That's correct. Actually, yeah, that's a very good point. Well, to be honest with you guys, I think the setup we have in the PV lab, especially for the large large panels or large modules, if you apply these measurements to small solar cells, actually they are very imprecise. Okay, for large area modules, they're probably relatively okay, but for small solar cells, when you go down to small scale, when you work on solar cells, these like all these measurements, for large modules, actually they are very, very imprecise. So actually this is perfectly, the point where we do need to, look into the detailed, specifications and think about how we can improve the accuracy. Okay, but then actually this point I'm talking about here is related to what you were saying, that we do need to, somehow place a sensor here, that from the sensor we're getting 1000 watt per square meter. Okay, but then this problem here, from the edges, the light from the edges, even if you have a perfect 1000 watt per square meter, but then if you have light coming from the edges, the effective area or the effective irradiance you get here is going to be larger than 1000. So that's actually another issue. Okay, another issue you have to sort of think about. Is this okay?
Yeah, thank you, Doctor.
Yeah. So both requirements are important. First, like what Omar is saying, you have to guarantee that you're getting the 1000 watt per square meter on the surface. But on top of that, the solar cell, actually you have to somehow prevent the solar cell getting more irradiance than it deserves. So this is I think this is the conclusion or the idea we can take from here. Okay. So let's look at the calibration. The irradiance is a proportional, typically, as far as we know, to the current or the current density. So any fluctuation in the irradiance, that's going to lead to direct error in the current density. Okay, so as as Omar was saying, this is why it's important, that actually near our solar cell, we do need, so near our solar cell here, we do need to place a sensor that will tell us that whether we're getting 1000 watt per square meter irradiance or not from the solar simulator or from any other surrounding light source. Okay, so this is why typically the solar simulator or the measurement setup, it will come with a calibrated reference solar cell. So in this setup in the picture here, this is actually the reference solar cell, and this is actually the solar cell to be tested. Okay, to be tested. So this is actually the typical setup that you will see in many different labs. Okay, many labs. The reference solar cell is typically a simple solar cell. Okay, it's a simple solar cell. And then what we did before is that before they ship this reference solar cell to you, they will measure this calibrated solar cell under a very standard light source. Okay, under the standard light source AMS 1.5, 1000 watt per square meter, and then they will basically record how much current that we're getting from the reference solar cell. Okay, now if you receive this reference solar cell in the lab, they will tell you what should be the actual circuit on the STC. Okay, so basically before you do the actual measurement, you just need to read actually the current from your light source, from your solar simulator, and then you compare between them. Okay, if the actual current from your reference detector is smaller, then in this case you need to turn up the intensity of your solar simulator. If it's the opposite, then you need to reduce the current input to your solar simulator to reduce the intensity. Okay, and then you need to keep adjusting until they finally equal each other. And then at this point, we consider that the irradiance we're getting from our solar simulator is matching with the standard condition, with the 1000 watt per square meter condition. Okay, so this is typically a quick calibration we need to perform before each of the measurement typically. Okay, and then afterwards you can do the IV scan of your solar cell, and then you could say that this is within our best capability. This is actually the most precise measurement we can do. Okay, so that is actually the reference solar cell. there is a very important requirement for the reference solar cell. Okay, the requirement is that your reference cell, ideally speaking, should respond actually to the wavelengths or to the same wavelength range as your solar cell to be tested. Okay, so they should respond, both of them, they should respond to the same spectrum range. Okay, so how can we guarantee this? You know, if you go back to the calibrated solar cell setup, you can see that there is actually for component number 2, this is actually an optical filter. Okay, an optical filter. So actually, when they sell the calibrated cell, they sell actually the calibrated solar cell based on the wavelength range that you desire. Okay, so if you want to work on a specific solar cell with the specific range of wavelengths that you have a response, then they will adjust the optical filter so that only this range of light they will go through the reference cell, and then your reference cell will only respond to this range. And if you do calibration within this range only, you will get the most precise results. Okay, you'll get the most precise results. And then, you know, if you do not pay attention to this requirement, this actually can create some problem for you, or it can create a very big error in your measurement. Okay, so for example, you know, if we look at, let's say, a organic solar cell that's made of the PTB7 polymer, it is only responsive actually to this range of actually the solar spectrum. Okay, roughly speaking, the band gap is around 670 nanometer, less than 800 nanometer. So the solar cell to be tested will only respond to this range. Okay, you only respond to this range. Now think about it. If somehow your detector, your reference solar cell, is only responsive to this range, okay? In this case, you know, no matter how you calibrate, it's not going to help with your solar cell measurement, because you know, you're talking about different things. You are calibrating the system at a completely different range. Okay, so this definitely, you know, to answer the question here, this definitely will lead to errors. Okay, so even if they have some overlap, you know, but ideally speaking, if you want to minimize the error, they should have a perfectly the same range, you know, between the solar cell to be tested and the reference cell that you use for calibration. Okay, so ideally speaking, if you are testing the PTB7 solar cell, then when you order the reference solar cell, you should specifically mention that the reference solar cell will only respond to wavelengths less than the same range. Okay, so that within this range, you will get the most precise calibration, and that will give you the minimum error. Okay, so this is actually I think the additional requirement here. Now, regarding the last requirement, you know, I think the consideration number 3 that we mentioned in the measurement, the last consideration is related to the solar cell area. Okay, to the solar cell area. The solar cell area, remember, we have to know the solar cell area if we want to measure the current density, and if we want to measure from there the efficiency. Okay, so basically they are related to each other directly. Okay, and specifically, you know, in the current density, you have actually the inverse of the solar cell area. So if your calculation, if your measurement of the solar cell area is, for instance, if you have a 10% error, you estimate the solar cell area to be 10% smaller, which is very common, because if you deal with the small solar cells, 10% error actually is quite common. Okay, but then if you think about it, how much would this cause inflation in the current density and also the efficiency? Actually, if you do 1 minus 90%, okay, 1 over 90%, this actually will go to 111%. Okay, this will go to 111%. So this means that you will see immediately a 11% inflation from the short circuit current density and also from the efficiency. Okay, so this is actually quite important for you to know that you do need to determine your solar cell area accurately. Okay, so here actually the photo here is actually a sample I made a couple of years ago. This is a organic solar cell. Notice the ruler that we have here to give you the sense of the scale. Okay, and then, you know, how big is one solar cell in the picture? Actually, each solar cell is roughly speaking from the tip of the finger here. Okay, so roughly speaking, the solar cell here is actually in millimeter range. Okay, if I remember correctly, those solar cells are 2 by 3 roughly millimeter each. And then think about this. If you cannot determine the area accurately within millimeter range, it's actually very easy for you to have a 10%, 20% error. Okay, that is one thing. Another challenge is that even if you set the parameter, you set the pattern or the electrode to be 2 by 3 millimeter, but then the end result from the fabrication will always have some fluctuation. Okay, these patterns or these shape that you see here, they were produced by a deposition method. The deposition method basically goes or is deposited through a opening. Okay, imagine that we have a piece of stainless steel here, right? Stainless steel here, and then there is an opening, and then we're going to deposit the shiny silver through this opening, and that will create actually the pattern that you see here. Okay, but then depending on the accuracy of the process, sometimes you will create actually a bigger pattern, sometimes you create actually a small pattern. Okay, so naturally there are some fluctuations here, and considering that your solar cell is so small, so it is very easy for you to end up with a certain error here. Okay, and that is something you should pay attention to, and you should try to minimize the errors in your measurement and also in your fabrication. Okay, so that is actually the other side of consideration for solar cell area. And then the final consideration I would like to mention here is actually what I actually just showed you earlier, that even if you perfectly measure the solar cell area, even if you fabricate the perfect area, the solar cell area is precisely the same as your fabrication technique determines. But then during the measurement, there may be some other issues. The other issue is that typically the solar simulator will give you a larger illumination area compared to the actual solar cell. Okay, but then the problem is that if you just measure as is with the fabricated solar cell, some of the irradiance, some of the additional irradiance, they may enter the solar cell, and that will cause additional current from the solar cell. Okay, but at the same time, you thought that you are still using 1,000 watt per square meter irradiance, but the real irradiance, if you calculate the optical power divided by the solar cell area here, this will be larger than the STC irradiance. Okay, so this actually will also create the inflation in the solar cell performance. It will appear that the solar cell is very efficient, but in fact, it's not that efficient. It's not as efficient as you were measuring. Okay, so somehow we need to stop this edge, incident irradiance. Okay, we have to stop actually the additional light from the solar simulator from entering the solar cell. Okay, how can we do that? Typically, we can use a so-called shading mask. Okay, shading mask. So basically, if you cover the edge of the solar cell, because technically this is only the area of the solar cell, okay, with some dark material, and to absorb the additional irradiance. In this way, you will get precisely or almost precisely the intended amount of irradiance entering the solar cell. Okay, so this is actually the idea here. Questions?
So
Yes.
the red one is the solar cell, and what is the blue one in the figure?
The red one is the solar cell, and typically the solar when you produce especially thin solar cells, they are very thin. So by themselves, they cannot exist independently. So typically, what you did is that you produce the solar cell on a piece of substrate. Okay, for silicon is not a thin solar cell, and the wafer is very thick. So that's why for silicon solar cell, we can just use the wafer, and all you see in silicon is just the wafer, and then we do different modification on it. But then for thin film, typically you have to use a substrate as a sort of like the support or the holder for the material, because the red layer is very thin. Okay, and very typically we use a glass as a very common substrate. So the glass will be the one holding or supporting the red layer. But obviously your substrate, your glass substrate, typically will be larger than the real solar cell material layer. Okay, so that is actually the glass substrate here. and can show you one example. So this is actually an example from the so-called dye sensitized solar cell. This is one of the 3rd generation solar cell. Okay, as you can see, this is actually the glass substrate, and then onto the glass substrate, they will produce the solar cell layer here. So this is actually the, you could say this is the what they call the active area of the DSSC, of the dye sensitized solar cell. Okay, but then the problem is that if you just measure, if you just do measurements on this solar cell directly, if you look from the cross section, this is the glass, and this is where you have actually the solar cell area. If you do just measurement like this, right, typically the light will come from the glass side. Okay, but then the problem is that because the glass will be able to reflect the sunlight, so some of the light actually will be entering the solar cell material, and that will give you additional current from the solar cell, which is actually an error. Okay, so the solution is that you try to cover actually the solar cell area, or maybe even smaller area, and then you leave just a square opening. Okay, so the square opening will define exactly the size, and then you consider the solar cell area to be the size of the square instead of the size of the circle. Okay, and that would be more precise because from the opening you receive exactly this amount of irradiance. Okay, and then like an improved version of this is that you also like to cover the edge of actually the substrate, because if you cover only this part, okay, sometimes it's not enough because you may have irradiance from this side entering actually the glass. So ideally speaking, you also like to cover the edges of the solar cell completely, okay, so that there are no possible way for light to enter the solar cell from the side. It can only enter actually from the opening here. Okay, so that's actually the example of a shading mask in Dyson solar cell, and this is one of the example you will see actually a lot in the real measurements. Okay.
But Doctor, this will add even more losses. I mean, the glass, even though it has like maybe transmittivity of maybe 96 to 98%, some of the light that is coming from the sun simulator will be absorbed or reflected, and maybe
Yep.
some part of the spectrum will be reflected or absorbed. So this will add even more errors in the measurement.
That's correct, but usually we do not consider the losses in the glass as an error, okay? Because you cannot fabricate the solar cell without the glass. The glass has to be always there. So any losses in the glass, it's not a measurement error. It's actually the losses that you already have, you naturally have in thin solar cell. With the thin solar cell, typically you have to always use a transparent substrate, and typically we if you want to improve your performance, yes, we could try to go for a more transparent glass. We could try to reduce the absorption in the glass, but typically we do not consider this as a measurement error, because if you deliver your solar cell, we consider the solar cell as a black box. Okay, so any losses happening inside, this is actually your problem. This is the solar cell's problem. This is not the measurement setup's problem. What is the problem? Additional problem is that if assuming that we have the black box here, but the black box is getting more irradiance than the 1,000 watt per square meter, then we consider this as a measurement error. Okay, so I just want you to understand that we're talking about slightly different things here. Okay.
Yeah, I get your point. Since the glass substrate is always held there, it's a part of the solar cell. So
yeah,
it's not
so you always have these losses, and the I think the challenge is that how you can reduce the glass losses. But at the end of the day, this is not due to measurement error. Okay, this is actually part of your limitation with your solar cell.
Doctor?
Yes, go ahead.
I also noticed from your earlier image with the reference cell side to side with the solar cell,
Yes,
that they're using very thin wires connected to the tiny solar cell. Like we need to consider the ohmic losses for the wires, and at the same time, like the connection is not perfect between the solar cell and the thin wires.
Yes, we do. We do have to consider that. But given that the solar cell we're using here is very small, what we can do is that typically we could try to figure out if we provide a very good conduction, very thick layer of wires, we could sort of measure the for instance the resistance of the solar cell, and then you can indeed separately you can measure the resistance from the wires, and then you could try to compare between them. Is the wire resistance, let's say, less than 5% or 10% of the solar cell resistance? If that's the case, then typically it's not a big issue. But you are correct. The wire resistance, the connection resistance, these are also factors we have to consider if we want to do absolutely, precise or correct measurements. So that's also a very good point actually to bring up.
This wire resistance will be represented as a drop in fill factor, right?
Yeah, typically it will go directly to RS. It will go, it will be added to the series resistance. Yeah, but then yes, you are right. If you have a significant wire resistance, this will affect your IV characteristic because the more RS you get, the more shape that is changed that you are going to see. But then if we do not consider the wire resistance, we cannot really tell that the change is it because of the solar cell itself or is it because of the measurements. So it's actually also very important for you to make sure that all the connection, all the cables, they are very conductive and they are much more conductive compared to the solar cell itself.
Yeah. Okay. Thank you.
No worries. All right. So let's. I think that's basically all the slides. I prepare for the efficiency measurement. So hopefully, through these slides, now you begin to have I think a clearer picture about what you need to do to guarantee that the efficiency measurement for solar cell is as precise as possible. Okay, so as you can see, we cover the major points I think in these slides, but yeah, additional considerations, like the wire resistance, like the lighting from the surrounding lamps. These things also they will contribute to errors. So there are actually even more considerations if you want to do an absolutely correct or precise measurements. Okay, but hopefully these considerations they will be enough to get you started, and I hope that you begin to see or you begin to think about for instance the setup we have in the lab and what from what aspects we can improve the accuracy, we can improve our results. Okay, and later if you need to run any measurements in our PV lab, you will know from where we can start to improve the accuracy. Okay, so that is I think the idea for this part of the chapter here. All right, so and then the second part of this chapter, I would like us to take a look at how the quantum efficiency can be measured. Okay, we talked about quantum efficiency in the last chapter. It is a very useful parameter to know for a certain solar cell. But then in reality, in practical situation, how do we measure the quantum efficiency? Okay, so let's try to look at this part. So from the definition, we know that quantum efficiency, or let's start from the external quantum efficiency, it is the number of usable electron and hole pairs, right, or the NEHP, divided by the number of incident photons. Okay, remember the keyword here is incident. We consider all the photons incident into the solar cell, and then we use the total number in the calculation. Okay, quantum efficiency, again, it is a function of wavelengths. So typically, you have to, at a certain wavelength, you have to consider how many electron and hole pairs are generated at this wavelength incidence, and then you have to also consider at this wavelength from the light source how many photons per second that we are getting, or per second per square meter that we're getting. Okay, so that is the definition we learned before. So basically, this means that if you want to determine the quantum efficiency, we have to find a way to determine these two parameters. Okay, these two parameters. So for the electron and hole pairs, we mentioned before, this is directly correlated or related to the current. Okay, to the current, because whenever you have the current is precisely charge, basically charge per second. Okay, charge per second. And then if you take the charge per second divided by the value of the unit charge, and then you will have actually the number of electron and holes also per second. Okay, also per second. So this is actually typically what you need to do. We need to measure the current from the solar cell, but keep in mind that this should be under a single wavelength. Okay, under a single wavelength illumination, we measure how much current we're getting, and then divided by Q. That will give us the number of electron and holes per second. Okay, and typically by convention, whenever people mention quantum efficiency, external quantum efficiency, if there are no additional description, by default, we will be measuring the current at the 0 volt. Okay, so because at 0 volt, we are getting the maximum current, that is the short circuit current. Okay, short circuit current. Of course, if you read papers, sometimes people also study the quantum efficiency at the certain voltage, and they will serve a certain purpose. But typically, we're talking about the general case. In the general case, we just measure the short circuit current from the solar cell. But also remember, it should be under a single wavelength. Okay, it should be under a single wavelength. And then from there, we can find the NEHP. Okay, we can find NEHP. Now, what about the second parameter, the number of photons? The number of photons per second, remember, this is related to the irradiance or to the spectrum irradiance. Okay, so we do need to find a way to measure the spectrum irradiance at this wavelength. And if we have this spectrum irradiance information, we simply need to divide this irradiance by the energy of one photon. Okay, so this is actually similar to the first example we showed today. The calculation from silicon solar cell under 600 nanometer irradiance. Okay, so it's roughly the same idea. And using the irradiance divided by the photon energy, we can find the number of photon per second. Okay, the number of photon per second at this wavelength. So this is actually the main idea. But then in real measurements, we still have some difficulties. Okay, we still have some difficulties. For one thing, typically the spectrum irradiance is not easy to get. Okay, it's not easy to get because it requires that you run another measurement, but this time not with the electrical measurement, but this time with the optical measurement. And as we know, typically optical measurement is more difficult to do, and this means that also your equipment needs to have an electrical measurement part as well as an optical measurement part. Okay, so this actually will complicate actually your system, will complicate your setup. So the question is, are we able to come up with an easier setup that consists of only electrical measurement, that we need to only do electrical measurement and we can obtain the quantum efficiency? There is a solution. Okay, there is a solution. The solution is actually very similar to the previous solar simulator measurement we talked about before. We just have to use a reference quantum efficiency detector, okay, or a reference solar cell. It doesn't matter. And then what do we need from this reference? Basically, from the reference solar cell or the reference detector, the quantum efficiency should be already known. Okay, so before they send the detector to you, the reference to you, they will measure the exact quantum efficiency of the reference at the supplier facility, and then they will provide this for you. Okay, they will send this to you. That with the reference here, we have a quantum efficiency with the wavelengths, and this is for the reference. Okay, this is for the reference. So they will send this information to you at a certain wavelength. If this external quantum efficiency is already known, then actually we have automatically the same equation that we had before. Okay, so the reference solar cell I short circuit, okay, divided by Q, and then over the photon energy, considering also the irradiance, that will also be known. Okay, that will also be known. So this is the idea. Now, if we have if we use the reference to measure under two different light sources, okay, to measure under two different light sources. So this is actually from the by default we were saying that this is actually from the standard light source. Okay, standard light source. However, if you do a measurement under another light source, then obviously the quantum efficiency for the reference will be fixed. Okay, the quantum efficiency for the reference will be fixed. But then, of course, with another light source, the spectrum irradiance will be different, right? Because a different light source typically will have a different spectrum irradiance. But because the quantum efficiency is fixed, so from where you are going to see the difference, you are going to see that with a different light source, the current or the short circuit current that you are getting from the reference, it's going to be different. Okay, it's going to be different. So from the current, you can tell that actually the light source we're using is different. The spectrum irradiance that we're using is different. Okay, so that is actually I think the one of the things you can see from the reference. Now another thing, if you use the reference and your sample solar cell, okay, under the same light source, okay, what is the other conclusion that you can draw here? If these two devices, they were measured under the same light source, so actually you are talking about the same spectrum irradiance, okay, the same spectrum irradiance. So at this time, if you know already the quantum efficiency of the reference solar cell, okay, so simply the quantum efficiency ratio between the sample and the reference will be directly proportional to the ratio of the eye short circuit that you were getting from both devices. Okay, so this is actually the eye short circuit we're getting from the sample solar cell, and this is the eye short circuit we're getting from the reference solar cell. So simply the current ratio between the two devices will be the ratio between the two quantum efficiencies. And since this is already known, we can already find out immediately the quantum efficiency of the sample. Okay, and that is actually the method typically we use in the quantum efficiency setup. Okay, instead of measuring the spectrum irradiance, which is typically more difficult to measure, we will just compare between the currents of the sample and the reference, and then from there we find automatically the quantum efficiency of our sample. Okay, so typically the external quantum efficiency measurement has two steps. Okay, so we typically have to do two measurements. The first measurement, we will measure actually the reference detector only, and then and then we're going to record exactly how much eye short circuit we're getting from from the reference. Okay, so basically at the one wavelength we will do one measurement. So you can imagine that instead of one current, we're going to get a profile of eye short circuit versus lambda. Okay, and this is the eye short circuit reference versus lambda. So we are going to see a profile like this. At a certain wavelength, we obtain a certain amount of current. Okay, and then we're going to repeat the measurement for the sample solar cell, and this time we're going to obtain the eye short circuit of the sample versus lambda. Okay, so we're going to get another profile. Okay, we're going to get another profile. So what we're going to do is that at a certain wavelength, okay, we're going to take the reading from both the reference and the sample. Okay, and then we're going to do the ratio here. Okay, we're going to do the ratio here. And since this is already known, right, this is actually from the supplier, it's already known, then we can, we will read also from the same wavelengths, how much is the quantum efficiency here, so that immediately we can find the sample quantum efficiency. There was one question, please.
Doctor, so the quantum efficiency of the reference cell is constant even if I'm using a different light source?
Yeah, that is that is usually a approximation, but it is an approximation that is usually accurate within a certain range of irradiance. So if your light source is not extremely strong or is not extremely weak, it's a normal light source, then typically within a certain range of irradiance, the quantum efficiency of the same solar cell will typically be constant. Okay, so here, yes, we're assuming that the quantum efficiency of the same solar cell will be the same under two different light sources. This is usually a reasonable assumption. Okay, this is usually a reasonable assumption.
Okay, thank you.
Doctor?
Yeah, no worries. Yes, go ahead.
Why are we using current? Why shouldn't we use current density? Because maybe the reference detector is not the same size as our cell.
Actually, that you are exactly correct. You are exactly correct. So to be precise, yes, we do have to actually in the slide actually to be using current density. You are exactly correct in that. The reason I wrote this equation because I didn't want to complicate too much, but you're correct. We should be using J here to be technically correct. Otherwise, if we want to keep the current, the I here, we have to guarantee that these two devices, they have the same area. Okay.
Okay, thank you.
Yeah. So for that, you're exactly correct. We should make sure that they have the same size, the same area, and then from there, we can always find the ratio. Okay, can always find the ratio. So this is actually the I think basically the conclusion we have here. To find actually the quantum efficiency from the sample. Okay, from the sample. So simply you have at each wavelength you have to do a ratio between the currents and then multiply by the reference quantum efficiency, and then you have your sample quantum efficiency. Okay, but of course, regarding the measurement, there is one requirement. The requirement is that the requirement. Okay, what is the requirement? So the question is, can we use directly the solar simulator for the quantum efficiency measurement? Will we be able to, let's say, just plug in a xenon lamp and then we run the quantum efficiency measurement? Is it possible? All right, try to think about it. What is the requirement for the light source in quantum efficiency setup? There's
no requirement?
There is a requirement. So I'm trying to ask you if you can let me know, what is the requirement that you think for the light source in the quantum efficiency system?
It needs to be stable and temporally stable and low spectral change. The three conditions we have.
The three conditions, very good. But regarding, so the question is, can we simply use a solar simulator to measure the quantum efficiency? Is it possible?
Doctor, the normal sun simulator operates at various wavelengths. We have to use a monochromatic one.
That's good. That's good. That's precisely, I think, the answer here. Remember that all these parameters that we're dealing with here, the I short circuit, the quantum efficiency, they're talking about strictly under one single wavelength. Okay, so per measurement or per point of measurement, you should actually use the current on the single wavelength. Now, the solar simulator is a very excellent light source, that's for sure. But at the same time, it's giving us all the possible wavelengths at the same time. You cannot selectively choose one wavelength and then measure the current there with the solar simulator. It's impossible. Okay. So what we need is that typically, yes, we do need the white light source. But then for quantum efficiency measurement, typically we do not need exactly the air mass 1.5 light source. Okay. Typically any white light source will be okay. But then on top of that, we do have to use a so-called monochromator that will actually selectively let the certain wavelengths to go through. Okay, so here actually we have a range of different wavelengths for the spectrum, but after the monochromator, we have only one single wavelength, and then the rest of the wavelengths will be filtered. And with the monochromator, we can actually, after some time, after the measurement, we can shift actually to another wavelength and then do the measurement again. Okay, so slowly we can scan the full range, and then from there we can actually plot the final quantum efficiency plot versus wavelengths. So this is actually the key component here. We do need to have a sort of a control on the wavelengths. Okay, so this is something I would like you to know. Okay, so this is the difference. This is the difference versus the efficiency measurements. So this is the typical setup for a quantum efficiency system. Okay, notice that we have two samples inside the system. One is the reference, one is the sample solar cell. Okay, so typically we will do the measurement two times. You will shift either the solar cells, the reference for the first measurement, and then you rotate the PV device or the sample for the second measurement, or the monochromator will be moving, and then you can measure two times. From two different devices, and then on the PC, if you have a direct data access, you can simply do some data processing. You calculate the quantum efficiency at each wavelength, and then you add them up, you connect them together. Okay. There are some additional components that probably you're seeing here. For instance, besides the monochromator, we have also actually another device here that's called a chopper and the filter wheel. Okay, and then here we have a locking amplifier. So probably we will leave this for next time. We'll come back to this next time to talk about the reason that we need to have a chopper and optical filter or locking amplifier inside. Okay, so for today's lecture, is there any more questions? Anything that's not clear you want me to explain it again before we conclude? Yes, go ahead.
For all what we talked about is for one cell. So do we have the same technology and the same calibration for the modular size?
For module, yes, there is the possibility, but again, the quantum efficiency is a parameter that's not dependent on the size. Okay, so instead of measuring like a large area quantum efficiency, why not take a small piece of the same material and then you measure the small solar cell? Because theoretically, the quantum efficiency for the small cell will be the same as the large module. Okay. But then you are right. Actually, there are some setup that will let you do a large area quantum efficiency measurement. I think I went to the solar park in Dubai one time. They have a research center there. So there they do have like a setup or a system to measure the panel quantum efficiency. But usually that setup is actually very, very expensive. Okay.
But doctor, as you know, the organic solar cells are losing part of their efficiency for modular size.
That's true. That's true. Yeah, that is correct actually. So yeah, if you want to demonstrate large modules, because considering the performance will be lower, yes, it makes sense actually for for that case to measure the large area quantum efficiency. But you could try to search about it. Typically for large quantum efficiency setup, those are very rare, and also I think they are very expensive typically. Okay.
And doctor, the specification we read behind the solar panel, are those for one cell or for the panel itself?
Typically for the panel. So if it's a label behind the panel, it's for the whole panel. So they measure the whole panel current and the voltage, and then they calculate the efficiency and things like that.
Yes, I got it. Thank you, doctor.
No problem. I think you asked another question before. Do we need a specific wavelengths? Is this talking about the quantum efficiency system?
No, I was answering your question for the.
Okay. Yeah, that's correct. Yeah, sorry, I missed that. Yeah, but that's absolutely correct. We need the monochromator here. Okay.
Okay.
All right. Any further questions, ladies and gentlemen? If not, I think we're good for today. Thank you, guys, for attending. And on next week, Tuesday, I think we're going to have a in-class quiz on chapter 1. Okay, so don't forget about that. Just be prepared. Okay, and then have a nice weekend. I'll see you guys. Thank you.
Doctor, about the quiz, is it going to be exactly at 11?
I don't think so. I think my preference would be to do like maybe half an hour or less than half an hour lecture, and then the remaining half an hour approximately we will be giving you for the quiz. Okay, so it will be available on Blackboard after some time from 11.
Okay, thank you.
Yeah, no worries.
Doctor,
yeah, go ahead.
What about the midterm date?
The midterm, actually, I'm trying to plan the before, but I think for the moment it's not clear about how we are going to do the midterm. I mean, the university is still mentioning physical exam, but also there is a chance that we go online. Okay, so I think the midterm has 2 weeks of duration. Would you guys prefer that we do the midterm in the first week of the midterm or in the second week of the midterm period? Any suggestions?
Maybe because because our instructors didn't decide the midterms yet, also, so we don't know. We can't
Okay,
decide.
I see. For if we do online exam, you know, to be simple, I think we can try to do like a, you know, we can just use one class time to do the midterm if we do online. Okay, so that in this way there will be no conflicts.
Yeah, that's good.
Yeah, that would be my suggestion if we do an online exam. So for one class we will be doing the midterm. Okay, so that you guys will not have any conflicts. Yeah, so if you have any suggestions, or if you have any preference, or if you have already any midterm already, you know, they announced the timing, let me know. But otherwise, I'm thinking maybe we can try to use the second week of the midterm, and then we do the you know, we do the midterm exam. Okay, I think the midterm starts from 18th of October. That's the first week, and the second week starts from 25th of October. So maybe maybe the Tuesday of that week during the class, we can do the midterm if we go online. Okay, so yeah, so for the moment that's my plan, but yeah, feel free to let me know if you have any suggestions. All right, so otherwise, if there are no more questions, I think that's it for today. Again, thank you guys for attending, and have a nice weekend.